Hi everyone. Today I want to talk about inverse trig expressions. There's a lot of information in this video, so I'm going to try to keep it as succinct as possible. Just when you thought the unit circle was gone, here it is again, rising from the ashes. It's not gone. In fact, it's worse than ever. So, you're in the way. Inverse trig requires your pretty decent knowledge of the unit circle. Now, when we talk about inverses, you may recognize that term, inverse. It just means opposite. So when we talk about inverse functions, what we really do is we just flip the x and the y. You can't see my hand motion behind this thing. We just flip the x and the y coordinates and we would graph another function. So quickly, examples. Let's just say I have a function on the coordinate plane that has an ordered pair on it that's 7, -3. Well, its inverse is also a function, or must also be a function, and its inverse would have the coordinate -3, 7. All right, so we're just literally flipping things around. And it's going to be the same exact idea with the trig functions, but there's a lot more to it than just that. So here is an example that we're going to talk about, and we're going to continue the process throughout the video. What is the inverse cosine of √2/2? And that can also be written as what is arc cosine √2/2. So we can have our traditional inverse with kind of like a -1 as the exponent, or we can have arc cosine, or arc tan, or arc secant. They're all the same. So whether you see this top first part or this second one, it doesn't make any difference. It's actually just the same exact process, right? Now, think about this, what it's asking us. Usually when we ask what a value is on the unit circle, we would say like, what's cosine of some degree measurement, or what's cosine of some radian measurement? And our answer would normally be √2/2. We're just flipping that around. So this answer, and cosine we're going to get to in a second, if I'm looking for √2/2, I'm literally just going to change around how I look. Well, √2/2 is at pi/4. So the answer to what is cosine, the inverse cosine of √2/2, we are going to actually have pi/4 or 45 degrees, but we really want to just leave the answer as a radian. Now, there's a question that comes up with this, right? Because aren't there two cosine values at √2/2? Yeah, that's how we get to this nonsensical thing that we're doing. And we're going to get to that very shortly. So we have a major problem. And the problem is that there are going to be two values on the unit circle that give us exactly what we're looking for. Just like our last one, cosine happens twice in the unit circle at √2/2, right? It happens at the 45 degree mark and it happens at 315 degrees. So how do we know which one we're looking for? Well, that's where domain and range come in. Earlier in the video, I had mentioned about how there's a function on the coordinate plane. Its inverse must also be a function, or for us to be working on one-to-ones. That phrase one-to-one is really important with trig functions. So we absolutely need to have our inverse trig functions as functions. They cannot not be functions, and I'm going to explain that right now. Here's the graph of cosine x. Its domain is all real numbers, but its range is -1 to +1. Now let's think about what inverse means. Inverse means I would be graphing this in the opposite manner on another part of the coordinate grid or another coordinate grid. And that's right here on my right. So our normal cosine function is here with all real numbers as its domain and its range at -1 to +1. But arc cosine, or inverse cosine, is way different. It operates very differently. It almost looks like a tangent function. It's not, but it just looks like one. Now, this is actually the exact graph from Desmos, and it doesn't go any higher than my point here on the finger, and it doesn't go any lower than that point either. And why is that? Well, because if it was to continue its process in this kind of circular pattern, it would not be a function. So it must stop, and it must be restricted within this domain and this range. So let's talk about that for a second. Here, the domain was all real numbers. But here, we can't have a range of all real numbers, because if the range is all real numbers on arc cosine, it would not be a function. It needs to remain as a function, right? So it cuts off right here before it would start to repeat, and it cuts off here right before it would start to repeat. Now, the domain is -1 to +1, because the range was -1 to +1. So you see how that kind of flip-flops a little bit. Now, because arc cosine only lives in this section of the graph, that is going to be how we can identify which number we're looking for on the unit circle, just like our first problem. So again, cosine and arc cosine. Same rules apply for sine. Here's sine of x. It's got the same exact domain and range as cosine does. But you see how arcsine, it just flows a little bit differently, but it still has that same restriction on the domain. But its range is different. So its range for arcsine is negative pi over 2 to pi over 2, right? And that's kind of how this works here, because our beginning point here in terms of, I don't want to say a period, but it cuts differently on the unit circle because our positive and negatives aren't the same exactly as cosine are, right? Let's continue. Tangent. And I'm not going to show you the other three functions because they follow similar patterns, but we'll get into it in a second. So tangent is here. Now, the one thing about arctan or inverse tan is that it will continue to go forever. Its domain is all real numbers. Its range, though, it will be kind of like sine, where it approaches negative pi over 2, and it'll eventually approach pi over 2. Right? So here is a wonderful graphic for you that's going to help you out with this process. Now, this is specifically for inverse functions. In quadrant 1, all 6 functions are positive. So if I ask for any positive value on cosine, sine, tangent, cotangent, secant, or cosecant, you're going to be in quadrant 1. If I ask you for a negative value on cosine, secant, or cotangent, we're going to be in quadrant 2. Now, again, when we talk about domain and range, that makes sense because cosine is alive, if you will, up here in quadrants 1 and quadrant 2. It's just negative in quadrant 2, right? Secant, obviously, because cosine and secant are inverses of each other, they have to follow the same path. Now, cotangent and tangent are a little bit different, which we'll get into, if not a little later, maybe in another video. And then in quadrant 4, sine, cosecant, and tangent will be negative, right? Now, there are no inverse values in quadrant 3. They don't exist in quadrant 3. And again, that's kind of where tan and cotan spoil the party a little bit, where they'd only be positive here anyway. So we'll get into that a little bit later. Now, here is the domain and range values, and there's a lot here, for all of our inverse functions. I'm not going to go through them all because I know you can read, but let's go ahead just really briefly through maybe the first 3 again. Cosine and sine have the same domain, and the domain for inverse would be -1 to +1, because you saw how those graphs were a little bit more stand-up-ish. That's not a word. But the range for inverse cosine is 0 to pi, where the range for inverse sine would be negative pi over 2 to pi over 2. All right. Tangent follows a similar pattern in terms of range, but the domain is all reals, just like cotangent. Now, secant and cosecant, kind of how, remember when we graph cosecant and secant, when we draw our roadmap in the middle, cosecant and secant exist outside of the roadmap. Well, the same rule applies here for its domain when we flip it or when we do its inverse. Its domain is going to be all reals except for that, and except for its range, right? Normally, or normal regular secant and cosecant, the OG secant and cosecant, its range is everything except for -1 to 1. But now its domain is going to be everything except for -1 to 1. So when we talk about inverse, we are literally flipping things upside down. Here are some examples. I put the unit circle here so we can kind of reference some things. So let's take a look and see what we got. It'd be awesome if you wanted to pause me right now also. So 1 and 4 have negative values. So reference back to what I did a couple of slides ago on where to look for those. Pause me and I'll come right back with the answer. Okay, you're back. Here are the answers. You probably got a couple of them wrong, and that's okay. Here's why. Let's go to 2 and 3 because they were pretty straight up. Sine or inverse sine of 1/2. So I'm looking for where the sine value or the y value is 1/2, meaning what coordinate part of y gives me a 1/2 value. Well, that's going to be at pi over 6. And I know it's pi over 6 and it's not negative pi over 6 because there's no negative in front of this 1/2. So I'm looking for a value in quadrant 1 here because that's a positive 1/2. It's got to be pi over 6 or 30 degrees. Number 3, also straight up. I didn't ask for a negative root 2 over 2. So what value of cosine, or what radian measurement of cosine positive gives me a root 2 over 2, and that's at pi over 4. Now, let's go to numbers 1 and 4 because the negatives might have thrown you off. Where is inverse tangent -1? Well, remember the tangent is y divided by x. So I'm actually looking for where I can divide a number by itself that will yield me a -1. Now remember that only happens at one point or one set of points, and that's over the pi over 4 values, right? Or the multiples of pi over 4. So because I wanted negative though, remember that tangent, and my hand's gonna go over here, tangent is positive in quadrant 1, but it's negative in quadrant 4, right? So where can I get a -1 value when I divide my y over x value? Well, that's going to be at 7 pi over 4. So why is the answer not 7 pi over 4? Well, remember that it's negative, meaning I was going to go the opposite way on the unit circle anyway. So I'm looking to go in my negative direction, which means that I have to find the difference between my 2 pi value or my pi values and 7 pi over 4. So what did I have to do to get there? I had to go down, or negative pi over 4, to get to 7 pi over 4. So my answer is negative. So here's the rule of thumb. If I've got a negative value here that I'm trying to figure out, I have to go the other way. So it's almost like I'm counting the other direction, right? Example 4, it looks a lot worse than it actually is. Now, think about what cosecant is. Cosecant is 1 over sine, meaning 1 over y. I'm looking for where, and this is negative, right? And cosecant is going to be negative in quadrant 4. So where exactly can I get a y value that looks like it's got a 3 and a 2 and a root 2 and a root 3 or something like that? Well, that only happens once, right? And that only happens when I have a negative root 3 over 2, because that's a sine value in quadrant 4. That only happens one time, and that's going to be at the 5 pi over 3 mark. But again, I want a negative here. So I'm not going around to 5 pi over 3 the normal way we go. I'm going the opposite direction. So instead of going 5 pi over 3 units, I'm only going 1 pi over 3 units to get the other way because it's closer. But I have to go into the negative direction or in negative territory. Let's finish up. Things to remember about this video. Number 1, know the unit circle. If you didn't know it before, now's a great time to remember it. Number 2, you got to remember the new rules for the 6 trig functions. And the new rules for inverse or arc really are where are they positive and where are they negative. I think it makes it a little bit easier that you know that quadrant 3 is totally out of the picture. I can't have anything in quadrant 3. Now, if you can just figure out the other 3 quadrants, you're looking pretty good. And then the last one is, I couldn't see it because of the camera's in the way. Draw the unit circle. And I think it'd be really helpful to draw it on problems like this, because when you get problems like this, they're gonna be in packs, right? There's gonna be like 10, 20 problems in a row, probably. It's unlikely that you would ever get from your teacher like 1, 2, or 3 problems. So drawing it will pay off dividends in the long run. See you next time.